Hello, everyone. I am Noelle Bakhtian, the Executive Director of Lawrence Berkeley National Labs Energy Storage Center. My team and I are so excited to have you join us on today's virtual field trip all about decarbonizing the steel industry. As a note, this field trip is going to be recorded and posted on our website, secretlifeofenergystorage.lbl.gov. So what the heck is this field trip thing about? Well, Berkeley Lab, together with SLAC National Accelerator Lab, which are two of the Department of Energy's 17 national labs, have partnered to host this seminar series called Exploring the World Unplugged, The Secret Life of Energy Storage. This virtual series is designed really to highlight current and future uses of energy storage, which is one of the linchpins for catalyzing decarbonization with major implications to electrifying mobility, accelerating renewable energy deployment on the grid, enabling grid resilience, amongst many other uses. And we're making it fun by providing field trip-like experiences so that we can all learn together. Before I jump into today's field trip, I'd like to introduce my partner in crime from SLAC. Over to you, Johanna.
Hi, all. So I'm Johanna Nelson-Wecker. I'm a lead scientist at SLAC National Accelerator Laboratory. As part of the team that created this field trip series, I'm so excited to welcome you today. One of the reasons that we founded this series was to help the public and researchers alike get a good look at how energy storage is used in real life and to understand the opportunities and challenges that we need to address together. Back to you, Noelle. Have fun, everyone.
Thanks, Johanna. So each tour that we go on showcases a real-world application of energy storage, and we provide a discussion on related science and technology research as well. And this also includes an opportunity for you as the audience to ask your questions. So together, we're going to learn more about how energy storage plays a pivotal role across sectors. So let's kick off today's virtual field trip. I'm so excited about this one. We're going to be touring U.S. Steel Company's Big River Steel site, located in Osceola, Arkansas, to learn about the challenging energy needs of the steelmaking industry and explore novel ways that energy storage solutions like high temperature thermal energy storage or hydrogen storage could potentially enable decarbonization and help us accelerate clean energy deployment in this space. Another reason that we're really excited about today's field trip is that, as you may have heard, the Inflation Reduction Act signed into law last week by President Biden appropriates over $5.8 billion for a program at DOE that will support greenhouse gas emission reduction projects in industrial facilities. So let's get this party started. We are going to start things off by touring US Steel's Big River Steel site, like I mentioned, and we're going to be hearing from two tour guides. Our first is Dr. Kevin Zeek, who is a senior research fellow leading U.S. Steel Corporation's initiatives in both innovation and sustainability. And then I'm going to have him introduce Dan Brown, who's a senior vice president there when the time comes. After the tour, we will get a chance to hear from two Berkeley Lab researchers who work on supporting decarbonization of different industries. And after the tour, I'm going to provide introductions of Dr. Prakash Rao and Dr. Hanna Brunig, who are part of the more than 200 folks at the Berkeley Lab Energy Storage Center. We were hoping to have Mr. Jim Bell as well from US Steel, but he's not able to make it today, unfortunately. Near the end of today's field trip, we are going to have a live Q&A, so please be thinking about your questions that you want to ask our researchers and our tour guides from US Steel, and drop those questions into the Q&A box throughout the entire tour and presentation. And we're going to get to as many of these as we can during the Q&A session. Also, feel free to use the chat feature to introduce yourselves to our tour group today. We'd love to know your name, where you're joining from, and the first word that comes to your mind when you hear the words industrial decarbonization. So now we're going to join Dr. Kevin Zeek, who will kick off our tour of the US Steel Company. Over to you, Kevin.
Well, thank you so much for allowing me the chance to talk to everybody today about the steel industry and about US Steel and our Big River Steel facility. United States Steel was formed in 1901, over 120 years ago. We make 22.5 million tons of steel capacity between North America, our mini mills, our plant in Košice, Slovakia, and our tubular segments. We have over 24,500 employees worldwide. We're a $4.2 billion in net earnings, and we make over 1,000 grades of steel some of which are the most advanced steels in the world, leading to the lightweighting of vehicles and modern appliances and modern building structures all over the US and the world. Before I get started, just a quick background. We talk about integrated steel and the mini mill steel. Integrated steel starts with the iron ore being mined from the ground in Minnesota. It's Fe2O3, Fe3O4, hematite, and magnetite. And we take that iron ore and bring it down to our unit called a blast furnace. The iron ore is combined with coke, which is made from coal. It's a purified version of coal, which is pure carbon. So I'm sorry about that. There we go. Video is started. So we take the iron ore from the ground, we take the coal, which is turned into coke, and we convert it into liquid iron at 2,500 degrees Fahrenheit. We take that liquid iron, which has about 4% carbon, and we put it into a process known as a basic oxygen process. Supersonic speed of oxygen goes through, makes a milkshake. It converts the liquid iron into liquid steel. Steel is just low carbon iron, 3,000 degrees Fahrenheit. We cast it and then roll it into products. The mini mill side takes up to 100% recycled steel, and using electricity creates a plasma arc, melting that at 3,000 degrees, going into a specialized continuous caster directly into coiled sheet products. So the differences is iron ore to steel integrated, scrap to steel, the mini mill electric arc furnace, which Dan Brown's going to show you today. As far as sustainability goes, the integrated process is about 2 tons of carbon CO2 per ton of steel, and the mini mill is 0.4 tons of CO2 per ton of steel. And since this is an energy talk, in 2021, United States Steel actually consumed 103 million megawatt hours of electricity. That's a lot of power to make our steel, 22.5 million tons of capacity. You look at North America, 76 million tons. And at Big River Steel, 3.5 million megawatt hours for 2021 to make our steel. So we're very interested in decarbonization of the integrated process and reductions in energy and the carbon associated with energy in our mini mill process. So with that said, and a brief introduction, I'd like to turn this field trip over to Dan Brown. So Dan, take us on a walk through Osceola, Arkansas, where you are today.
Hey, Kevin, thank you very much. I appreciate that. As Kevin stated, U.S. Steel made the decision to acquire Big River Steel back in January of 2021. In doing so, as Kevin stated, also with a lot of good details and data, we have the most highly technological advanced steel plant in North America. And along with that, a really, really green footprint that's decarbonized a lot more than what the integrated plants for the last 100 years in the steel industry in the United States have done. So if you could please cue up the video for the tour. I'm going to walk everyone through the process here quickly as we go through a tour on Big River Steel in Osceola, Arkansas. Big River was built in 2014 and built the first, or had to roll the first coil in December of 2016. So what you're seeing here right now is our electric arc furnaces. As Kevin stated, we don't have blast furnaces, coke, iron ore. We use up to 100% recycled steel. On the left side of the screen, you'll see what we refer to as a scrap bucket that's filled with 190 tons of steel right now dropping into that furnace. So you'll see the bottom open up, you'll see the scrap bucket drop, and you'll see the scrap go into the furnace in order to melt that down into liquid steel. When this process happens, again, that scrap bucket is filled up with 65 to 70% recycled type steels from automobiles, washers, dryers, appliances, things like that. And the rest of the charge is anything from pig iron, hot briquetted iron, and other scrap that we use from around the industry. After that scrap's dropped into the furnace, and you'll see shortly, this is a split screen, by the way, that we're using, and you can see the operator on the right side is actually looking forward into the furnace. The furnace has a 1 electrode operation electrically that goes down into the furnace to melt the scrap. And you'll see on the right side the exhaust. When the furnace is closed up with the roof of the furnace, it'll contact on and seal up, so we take away all the emissions from melting the steel inside the furnace. This process generally takes about 20 minutes to completely melt all the scrap into liquid steel inside of the furnace. And then we have to get our chemistry right. We have to make sure the temperatures are right. And the bottom of the furnace has a slide gate system where we actually drain the furnace into a steel ladle after that's done. We average making heats here in approximately 35 minutes for Big River Steel. And again, 1/5 of the emissions and 1/5 of the emissions that integrated plants have throughout U.S. Steel or blast furnace operations amongst our competitors. You'll see the electrode go in right now to melt the steel. A lot of noise at that point in time. And then over the course of 20 minutes, that heat will become liquid steel for further operation into the process. I'll walk from area to area throughout our facility today. This video takes approximately 7 minutes. So the next stage of the operation, and if you look to the left, you'll see below the deck on the left-hand side, that operation is a smaller electric arc furnace, which we refer to as an LMF. It's a 3-electrode system. So the heat of steel that's being picked up by the crane right now will be taken out of there. That's a process heat of steel. On the left-hand side, after we get done with melting steel in an electric arc furnace and putting it in a steel ladle, we'll add alloys according to customer specifications. We'll add aluminum, manganese, carbon in some cases, aluminum wire. We'll add different alloys as part of the operation to further refine that liquid steel into customer specifications. At that point in time, after we get the majority of the oxygen out of the steel and make sure it's up to temperature and up to customer spec, we'll take that full steel ladle that's completed at the LMF and take that up to our casting operations and start to cast that into solidified steel. The caster itself, you'll see this ladle come onto the caster right now. It's taken up about 3.5 stories inside of the shop. That full ladle of steel is about 170 tons now of liquid steel. And that goes on back of the casting operation to a turret arm. That's what we refer to, what you see on the right-hand side of the screen. So there is a steel ladle that's being drained through the bottom on the right side of the caster right now. And this ladle will be loaded on from the other side. We have a continuous casting operation, which means once the liquid steel is poured out of the right side and that ladle is drained completely on the right side of the turret arm, you'll see the turret rotate and you'll see the other ladle go over and start pouring into the mold continuously so we don't lose the operation. You have to continuously fill up the mold. There's a tonnage box, which is a holding container really for liquid steel. So this ladle now is drained on the right-hand side. You'll see the operator rotate the turret to bring the full ladle of steel around, and you'll see a glowing orange shroud on the right-hand side that will be applied to the full ladle that's being swung around right now into position. So the ladle coming around towards you is completely drained now with 170 tons of steel, and we'll start to pour the new ladle of steel into the mold of the caster. Now that steel is poured into a mold. It's cooled with high pressure and large volumes of water at one time. So we create a shell around the steel, which is still liquid in the core, and we'll send that through the operation to get rolled at the hot mill. Now, this is just a picture of our tunnel furnace. There's not a lot going on here, but after we cast into what would be a solid state transfer bar that's 2.5 inches thick, it goes through a tunnel furnace to get to our hot rolling mill and to maintain its temperature, to maintain its shape, and to maintain its chemistry, and to maintain, to make it homogeneous temperature-wise throughout the bar. We keep it heated up all the way through the tunnel furnace as it's rolled through a series of rollers down to the hot strip mill. Now, when it gets to the hot strip mill, this is a 6-stand mill. This will get reduced step by step through all 6 stands. So you'll see the bar come through the mill right now. And as it transferred from one stand to the next, there's more pressure, the rolls roll faster, and they come down a little bit harder on that steel. So it may start out 2.5 inches thick. You may get down to, we roll as low as 0.57, 0.57 or 0.57 band gauge to the lightest thickness on this mill right now. We can make anything from 1/2 inch down to 0.57, and depending on the customer spec, again, it'll be rolled into that thickness. Now that bar will get rolled into a coil that can be up to 40 tons out of this facility, and those coils are taken for further processing throughout the operation of the facility. The hot mill that you see running here probably receives a bar from 2 casters approximately every 4 or 5 minutes throughout the operation during the day. And again, it's processed through the entire mill, hit with a large volume of water, and then cooled off and rolled into a steel coil at the end. Now, for further processing, our steel goes to various units. The unit in front of you is an annealing facility. And what the annealing facility is used for is for steel. It reduces hardness, it removes impurities, and makes properties for a steel coil, depending on the application. If it's automotive steel, appliance steel, if it's going to be made into tube or pipe, that steel is fired with high pressure hydrogen inside these stacks that you see in front of us. There's probably 3 or 4 coils on their side within the stack that you see in the center of the screen. It's covered with a base, and then it's fired up with hydrogen up to approximately 24 hours to hit those properties. So that's the complete quick tour throughout 7 minutes. I know there's a lot there. There's a lot more that happens obviously behind the scenes, but I'll turn it over to you, Noelle.
Awesome. Dan, thank you so much for that walkthrough. And I think we got to see more than we probably would have seen if we were there on site, given what we were seeing in the video. So thank you so much for that. I'd like to welcome Kevin back onto the screen as well, so we can have a little bit of a discussion about what we just saw. I also want to remind people that the Q&A portion of the Zoom webinar here is open, so feel free to be throwing questions in there for the Q&A portion at the end. So let's kick this off. You know, as the two of you know, the focus of this seminar series is energy, and more specifically energy storage. So let's talk more about the opportunities in this space. So first off, I'd love to start the chat with digging in a little bit deeper, Dan and Kevin. What are the day-to-day energy needs of your facility, like power, energy, temperature, thermal waste, duration, continuity, anything you want to share that might be helpful for folks to understand? And then what current technologies are you using to get there?
Well, I could start out, Dan, we typically use about 400 kilowatt hours per ton of steel down at Dan's Big River Steel for his electric arc furnaces. And as you can see, he has an arc on time where it creates that plasma to melt the steel, probably for 15 to 20 minutes of each hour. Is that correct, Dan?
Yeah, Kevin, that's correct.
So if you look at our footprint, about half of our CO2 comes from the process itself because it uses a graphite electrode to create the arc. Plus, Dan injects anthracitic coal to make a protective slag over the steel so that that plasma doesn't melt the walls of his steel furnace that's water cooled. So half of his emissions come from the electrode, the anthracitic coal, or the process itself, called scope 1, and half of his emissions come from scope 2, which is the electricity that is needed to turn that scrap into the molten steel. So by having emissions-free power available to him, we can actually take a process that's best on planet Earth today and cut those greenhouse gas emissions in half again.
Excellent. Dan, anything you wanted to add to that discussion?
Sure. Yeah, just a couple things, and Kevin covered it correctly. I mean, we're building another plant side by side to this plant too. That's the only other thing that I wanted to add. And this plant's actually going to be bigger. I said earlier that we have the most technologically advanced steel plant in North America. This will replace this one as the most technically advanced steel plant in North America. It'll be started up in 2024, and it'll probably use upwards between 500 and 550 megawatts. At that point in time, we will be the largest consumer from Entergy in North America from electrical power source for all the steel that we're going to make here. We're going to make 6 million tons. But to Kevin's point, our provider, where the bulk of it comes from nuclear energy, then on top of it, they have a footprint that's going to pure hydro. They're getting rid of all natural gas and coal fire energy sources into the plant. They're going to hydro, wind, and solar power completely across the board. And we're looking for opportunities with those to supplement also. So we really keep this out in front of us from a GHG standpoint, and there's a lot of opportunity here for sure.
Gotcha. Well, that's a good lead into my next question, which is let's start thinking about those sustainability goals again, Kevin, that you mentioned at the beginning. You know, your company is being very aggressive here. So could you guys talk a little bit about what are the short-term and long-term changes needed on the energy front? Like which solutions do you guys have already figured out in your plan and which are you still working on? And the reason I'm asking is, we have a lot of researchers on the line, for instance, that would be interested to see if there's still room for them to support on the research and development side of things.
Absolutely, there's room for everyone in this challenge. And when you look at it now, our short-term goal right now that we've published is to reduce greenhouse gas footprint by 20%. A lot of that is let's get our electricity much greener. Let's get our electricity much more emissions free. But beyond that, there's only 3 ways to reduce iron ore: carbon, hydrogen, and electrical. And there's programs, DOE sponsored, where you can do electrolysis, where you literally melt the iron ore and electrolytically separate the iron from the oxygen. The other way is hydrogen. Hydrogen can take the oxygen away from the iron ore, leaving you with pure iron. Dan mentioned that he is a consumer of something called direct reduced iron. The blast furnace takes iron ore, coal, limestone, and makes liquid iron. The HBI-DRI, hot briquetted iron, direct reduced iron process does it in a solid state right now using natural gas, methane. In the future, you can substitute pure hydrogen for the methane and have a 0 carbon footprint way of making lump iron from the ground. And then Dan Brown can use that in his process to reduce his carbon footprint even more. So the opportunities abound, but as some of the researchers will know, there are large challenges when switching from a natural gas fuel to a hydrogen fuel.
Helpful. Dan, anything you wanted to add to that one?
Sure. Yeah. And to Kevin's point, we look for all opportunities. I'll go again back to the plant that we're currently building that's going to be operational in 2 years. We look at everything forward in a forward manner that we can do right now. Low NOx burners, electric vehicles on site. Anything that we can do from that standpoint to eliminate and lower our footprint here. That's exactly what we're doing going into the future. So Kevin's absolutely right. It's probably twofold. We have a plan that rolls out to 2050, a very detailed, aggressive plan within U.S. Steel that we're capitalizing on right now from this standpoint. And we look at what opportunities exist to get lower and lower with every production line in every facility that we have.
And I might actually even pile on what Dan, you just said about we as a company, U.S. Steel, keep the capacity of over 22 million tons of steel. Our goal is to be net zero by 2050. And Dan's leading that effort with Big River Steel and the second mini mill that's coming online there. We've also, and I'm very proud of Dan's organization, we have joined a community called Responsible Steel with 12 principles that not only govern greenhouse gases and energy usage, but govern all things E, S, and G so that we become very socially responsible in our path to net zero. And very proud, Dan's the only North American facility that is now plant certified for responsible steel here in North America.
Excellent. Dan and Kevin, thank you so much for this incredible tour. We're looking forward to learning more during the Q&A. But now we're going to move to the next part of this session, which is hearing from 2 of our researchers in this space. So first up, let's join Dr. Prakash Rao, who's a research scientist in Berkeley Lab's Building Technologies and Urban Systems Division. Dr. Rao will be walking us through the big picture, so national data on industrial energy needs and providing his expertise on decarbonization of industry and manufacturing. He's also going to share some information from a recent national workshop in this space. So over to you, Prakash. I think you're on mute.
Sorry about that. Hi, all. Thank you, Noel, for that introduction. As Noel mentioned, I'm Prakash Rao, and I'll be giving you guys a high-level overview of thermal energy storage and its potential applicability in the iron and steel sector. And I recognize this is probably the toughest act to follow because having a tour of an electric arc furnace is pretty exciting, but I'll try to meet the excitement. Well, given that the theme of our talk today is decarbonization, I thought it might be instructive to start with where we stand as a nation around decarbonization. Our US goal set forth by the White House is net zero by 2050, which US Steel, you just heard, that's their goal as well, so right in line. But if you look here, this is from a White House report from November 2021, you'll note where we are with respect to that goal. So things are compared against 2005, which is about peak emissions shown in this graph of around 6.5, a little over 6.5 gigatons of CO2 equivalent. Currently, we're about 17% below that level at around 5.5 gigatons. And as you can see, by 2025, we want to drop an additional 10-ish%. By 2030, an additional 25-ish%, which will bring us down to about 3 gigatons, a little over 3 gigatons, and then cruise our way to net zero in 2050. And how does iron and steel play into that pathway? So here you're seeing the US economy-wide energy-related CO2 emissions. And as you can see from this chart, transportation sector is leading. These are your cars, your planes, trucks. At 37% of all CO2 emissions are attributable to the transportation industry. However, the industrial sector is 29%, the next largest chunk. And now the industrial sector includes mostly manufacturing, but as well it does include agriculture, construction, and mining. But when we break apart the industrial sector, we see that all iron and steel production in the United States represents 2% of all US emissions. Within the manufacturing sector, it's third behind chemicals and refining. But at 2%, it is a non-negligible amount of our US emissions and critical towards us meeting our net zero by 2050 targets. And as you can see, for context, you have food at 2%, paper at 1%, and some other energy-intensive industries as well for perspective. So how do we get to that the net zero by 2050 pathway? The same report from the White House from the chart earlier provides some pillars. The first being energy efficiency, which would reduce, of course, energy demand at the plants. Then decarbonizing our electric grid, going to green power generation with solar or renewables, followed by energy transitions, as they call it, which is going to hydrogen, low carbon fuels, electrifying processes, such as going from some of those integrated mills to the mini mills that Dan spoke of. Then there's non-CO2 reduction, so the other greenhouse gases, followed by pulling carbon out of the air, either through natural processes like trees and using land as a sink, or through carbon capture. And today we're talking about thermal energy, or at least I'll be talking about thermal energy storage. And I want to highlight where I believe it can provide facilitate two of these pillars in quite appreciable ways, specifically enabling deep energy efficiency improvements and facilitating electrification and adoption of low carbon fuels. I'll focus a little bit more on the energy efficiency one, given to stay within time limits here. But to step back again and just think about thermal energy storage conceptually, what it allows us to do is to decouple energy supply and demand by capturing and storing energy so you can use it at a different time or a different location than where it was generated and when it was generated. So conceptually, what this might look like is on the left-hand side, you have a carbon-free energy source that's available. So this might be excess solar from excess electricity produced by a solar farm, for example, that would otherwise be grounded or wasted. It might be a waste gas or an off gas or waste heat from a process that would otherwise be vented. It could just be the sun, right? Collecting more of solar energy, perhaps as a thermal source. And then collecting this energy into and charging a system, a thermal energy device. This charging could be through something like electric resistance heaters, if you want to convert it of the electricity into heat. It could be through heat exchangers, something like that. But then that energy is stored, the carbon-free energy is stored in a thermal energy device. These are things like waxes, bricks, to more advanced materials that are currently under development, hydrogen. And then there's a shift essential to the function and benefits of a thermal energy storage system. There's some shift either in time or place so that it allows it to be discharged when it's needed. So the discharge could be, again, a heat exchanger, could be heating hot water, could be making steam, could be burning it. And that allows for that energy to be used by the end use. So you've taken your carbon-free energy, which was generated in one time and place, and you have your end use, which needs it at a different time and or place, and you're able to use a thermal energy storage system to power that end use with carbon-free electricity, or sorry, carbon-free energy. So how might this work within a iron and steel plant? Not specifically here, but this is across the US iron and steel mills. This is data from the US Department of Energy and also charted by them. Here you're looking at the flow of energy in 2018 through to all of iron and steel. So iron and steel consumed 1,469 tera-BTUs of energy in 2018. And for context, the US economy is about 97,000 tera-BTUs. So you're looking at 1.5% of US energy use is for iron and steel making. Over 300, close to 400 tera-BTUs of this energy is lost even before it enters the plant. And this is getting to what US Steel was mentioning, some of the losses in power production for the electricity before it even enters the plant. But then once on site, you have 1,076 tera-BTUs, of which about half of it is lost, with a lot of it being to process losses as heat, for example, or off gases. And 545 tera-BTUs are actually used for steel making. So there's a couple things to point out here. One, there's a high thermal demand. So you see the fuel portion of this is 855 tera-BTUs out of 1,076, and the electric is 214, and some of that is within electric arc furnaces for heat. But the point here being that a steel plant, when you think about it, it's really a thermal plant. It's a lot of heat. Even the electricity is used for heat. So we need to be thinking thermal when we're thinking about decarbonizing the iron and steel sector. And in spite of probably iron and steel sector being one of the sectors leading the way in energy efficiency improvements and making huge capital investments to lower their energy costs and energy consumption, there still are significant energy losses just because how challenging steel making is, with a significant portion of it lost. And now, how can thermal energy storage potentially play a role in addressing some of these losses and improving or helping to decarbonize the operations? Here, we saw a mini mill process, but just as an exemplar, and the folks at US Steel talked about the DRI, the direct reduced iron process. But just as an exemplar, to show this is an integrated mill, which is a blast furnace and basic oxygen furnace combination in lieu of the electric arc furnace. Just to orient ourselves a bit, we have this chart is showing temperature in Kelvin, and I know that's a very scientific unit, but for those, just subtract 273, and that's Celsius. So that's your scale right there. And also a lot of lines here, but what I wanted you guys to focus on are the solid black lines, the thin and the not thin black lines. But what we see here is that while steel making is a very high temperature process, around 1500 C's, some of the peak temperatures, there are temperatures from ambient to 1500 degrees C, meaning that there are thermal needs spanning these processes, spanning the whole process. In fact, 48% of all process heat demand is below 1000 degrees C within iron and steel mills collectively now, not any specific mill, which allows for opportunities for not just high temperature storage, but also low and medium. So we can really be thinking about the gamut of thermal energy storage to perhaps preheat or reheat or supplementally heat things. The other thing is, as we mentioned, thermal energy storage looks at shifting in time. Within a blast furnace, basic oxygen furnace process, you have continuous operations and you have batch processes, which are highlighted with the blast furnace being continuous operation, meaning it's constantly feeding and generating liquid iron, and the batch process constantly, the basic oxygen furnace working in batches and charges, kind of like what we saw with the cradle and the electric arc furnace. So this allows for thermal energy storage to perhaps provide production buffers for the batch processes, or to kind of coordinate timing and again disconnect that supply and demand, which thermal energy storage does so well. Recently, the U.S. Department of Energy, Sandia National Laboratory, and other national labs hosted a workshop. This is in February of 2021 on energy storage for manufacturing and industrial decarbonization, Energy Storm. We had good representation from the steel sector, and we were able to talk quite a bit about thermal energy storage and identify some opportunities and industrial needs and needs from industry, excuse me. And so what I want to highlight is just some of the bullets there. Opportunities, speaking to the steel sector and attendees, all storage mediums have possible applications. Hydrogen can play a central role, both as a fuel and we heard in the reduction of iron ore. Other gas storage, we saw from one steel maker where they're storing off gases to provide a production buffer for about 30 minutes at an international steelmaking facility. Electrochemical storage, things like batteries, large batteries, to enable process electrifications. Replacing those integrated mills and going to mini mills, as Dan was mentioning, would really deliver carbon savings. But industry called out, hey, there's some things we need to do here. One of the things is storage needs to be safe, and then that was a big harp that the safety for storage. There's a large infrastructure required for gas storage because it's low density. And also to de-risk some of these investments, we need some pilot scale demonstrations that would help that early adopters could kind of share information and de-risk the investment and help others understand that, you know, this is okay, we can do it. And further, speaking of hydrogen with scale, currently our hydrogen storage and our hydrogen production is really not at the scale that we need for the scale when we talk about decarbonizing the iron and steel sector. There needs to be growth in that. And I just wanted to conclude with some of the types of ongoing research within the National Lab supported by DOE. It's across the spectrum. We're looking at things like analysis to help create research and development targets for energy storage performance characteristics, whether it be cost or size or energy density, those sort of things. Fundamental research to achieve those performance characteristics, such as novel materials. LBL, for example, has some research going on in high temperature energy storage. You're going to hear from Hannah about hydrogen. Manufacturing enhancements to produce new materials. So those materials that we identify that can achieve those performance characteristics, how do we manufacture them? Demonstration projects to de-risk investments, deployment direct to iron steel mills to help them with decision support, implementation, recognition for the good work that they're doing. Finally, evaluation to start to understand how are these technologies serving to decarbonize and where are things working. So I'll leave you with that. I want to thank you guys for joining, and Noelle, I'll hand it back to you.
Thank you so much, Prakash. That was great. Now let's join our second researcher, Dr. Hannah Brunig, who's a research scientist and the deputy head of the Sustainable Energy and Environmental Systems Department in Berkeley Lab's Energy Analysis and Environmental Impacts Division. So Hannah is going to be sharing some research projects in thermal energy storage and hydrogen space that have the potential to support industrial decarbonization at steel plants and beyond. Over to you, Hannah.
Thanks, Noelle. Hi, everyone. I'm so happy to be talking to you today because the steel industry is, while it's a great challenge, it's also one of the most important industries we have that society is literally built around. So working with the steel industry to understand the ways in which we can lower the impact of our demand for steel, which is such an amazing material, is critical going into the future. And we've heard from Prakash that there are ways that we can improve efficiency. There's lots of opportunities for taking the heat that's lost at the facility and somehow capturing it, storing it, and using it again for later use, whether at the facility, or maybe you could even do something that requires heat, like power direct air capture itself. I see Climeworks on the line today. So today I am going to be talking about novel energy storage technologies, including some more thermal energy storage as well as hydrogen. So right now, the big holy grail for energy is being able to have clean power anywhere, anytime. We have a lot of wind and solar, hydropower, other forms of low carbon energy. They don't always match when we need them or where we need them. So we're thinking about new technologies and new clever infrastructure solutions to either transport the clean electrons or another form, such as turn those electrons into hydrogen, a gas, and turn that into a means that we can transport. All in that, we need to understand what is the need for storing energy. So when we're looking at something like wind or solar that's intermittent, it's variable, it can't deliver 24/7. We are starting to set aggressive targets for energy storage so that we can charge them when we have excess renewables and deliver them when we need it, maybe at the middle of the night or when there's shortages in wind power. Now, oftentimes people think about batteries when we think about energy storage. There's a lot of research going on batteries to make them as even better than the ones we have today, to make them cleaner than the ones we have today. But batteries usually have their sweet spot less than or at 10 hours of storage. So if you have a facility that's operating at very large scales and needs reliability, that's often what industry contacts say to me. We need to start thinking about ways that we can store energy for longer than 10 hours. And that's where my research has really taken a focus, is long duration energy storage that has significantly lower costs, can store for more than 10 hours within a decade. That's the Earth shot that DOE has put out to researchers such as myself. So thermal energy storage, we got a little background with Prakash. I'll share a little bit more. It's the process of collecting thermal energy for later use in the form of sensible or latent heat or chemical energy. And if you've ever been to the Yuba River or another river where there's granite rocks, you sit on that rock, you might burn yourself. There is so much heat that is radiating back out of those materials. That's sensible heat storage. We also see that with chilled water systems. Those are old school technologies, but they aren't serving our current and new needs. They aren't as adaptable. They aren't as quick to respond. They might be costly. And so there's other new technologies coming out, such as materials that change phase, or ways to take the thermal energy and store it in a chemical form. So later, when you get those chemicals back, you actually release heat. Thermal energy storage has been deployed today. We see it at the concentrated solar power systems, the farms where you see all those mirrors concentrating that solar energy. For them to become a steady, reliable source of clean energy for the grid. They can't just have a few hours at a time that they're on off. So they rely on taking that energy, turning it into a form of heat storage in molten salts, and then taking the energy back out of those salts when they need it. And so the green shows that they can actually provide a really smooth delivery of electricity based on that. We're also seeing some very cool solutions come out for smaller buildings or little communities where you have seasonal storage. You have a lot of sunlight in the summer. You can actually store it underground and use it later in the winter to power your systems. Now, some of the research I've been doing is working closely with experimentalists who are developing new types of materials, basically new bricks, where you can not only use heat to basically heat them up, you can actually directly heat them with electricity. This is called joule heating. But there's a great challenge of finding that sweet spot of how costly can it be? What is the material going to be in terms of how durable it is to cycling on and off, going to handle those big swings in pressure and in temperature? How well does it conduct the electricity? And we're starting to see some really promising initial results on the capital cost associated with the technology, as well as the type of temperatures that we can reach with these materials very, very safely. So this is one concept that we found looking at a high temperature thermal energy storage system that is delivering heat to an end user. And in this case, we looked at iron and steel facility needs. So the system here is looking like a brick that's insulated. It's being powered directly by electricity, either when there's excess or when the grid is selling cheap electricity. And that can either be taken directly as heat through a heat transfer fluid, or there's starting to be emerging systems called thermophotovoltaics, which you can take that heat and turn it back into electricity. So boom, you've all of a sudden created a system that can serve both electricity and heat demands. We're finding this is over 98% efficient, it's safe, it's meeting the storage durations that are required, and very exciting news, we're actually starting to see that we can hit some of the cost targets that DOE challenged us with at 5 cents per kilowatt hour delivery when this is converted to electricity. So this is an emerging, very affordable form of storage that we're hoping will get out within the next 5 to 10 years. I saw Antora is on the line. They're a high temperature thermal energy storage company as well. So there's a lot of interest in trying to meet the needs of high temperature industries such as the iron steel facility. Now I'll switch gears with the last few minutes and talk about hydrogen. Hydrogen is only as clean and renewable as its source. Today, globally, the production of hydrogen from natural gas and coal is 2% of all of our primary energy consumption. On the flip side, that's great because we actually have a market for hydrogen that we can transfer to renewable green energy coming from electricity through an electrolysis process. What do we need to do that? Well, we need storage. We need hydrogen storage. The other thing with hydrogen is used by the industry to actually reduce the iron ore. It's not so common in the United States, but globally, a DRI furnace, a direct reduction iron furnace, takes a syngas, carbon monoxide and hydrogen, to reduce the iron ore. This process requires heat when you start to increase the amount of hydrogen used. So there's some trade-offs here. But we did an analysis looking at what is the need of hydrogen, what is the need for hydrogen storage, and how can we ensure reliability for this facility. We also looked at different technologies for hydrogen storage. Well, conventionally, you can compress it, you can turn it into a very cold liquid. These are not going to cut it. They're very expensive at these scales. They haven't been done before. They take a lot of land. There's a lot of losses with cryogenics. So there are new options, new materials and ways we can store hydrogen that I'm exploring through a Department of Energy program called HIMARC to understand how we can deliver hydrogen to these systems and store that at ambient conditions. Now, when I go out and talk to industry partners, often the terms they're using about what they need for electricity or hydrogen or heat, it's all in some quantitative, some very qualitative words and phrases and numbers and metrics. And my job is to translate all of this to what the experimentalists need to understand. And usually that's thermodynamics, kinetics, and capacity, storage ability of material. And this is exactly what was happening when we partnered with some companies looking at DRI furnaces to understand their needs. We did find, excitingly, that the material we looked at, methyl cyclohexane, can meet the cost potential of a large-scale geologic salt cavern storing hydrogen, which is today considered the most mature and cheapest form of hydrogen storage. So that was super exciting because now we can provide hydrogen right to you, right at your door or behind your gate, and deliver it. The challenge really comes from driving down the cost of this renewable electricity. And I'm excited to say we partnered with the Wind Office to look at ways we can custom tailor wind farms to meet the needs of the iron and steel facility. And finally, I'll just conclude by saying over the next 4 years, this HIMARC program is really key on partnering with industries in the iron and steel facility, as well as new startup companies making hydrogen storage solutions to help guide that research into the market at scale. Thank you, everybody.
Thank you so much for that, Hannah. Really appreciate it. So with that, that ends the researcher portion of our talk today. So I'd like to welcome Kevin and Dan back up, and we're going to move into the Q&A. So thanks to everyone who's been putting questions into the Q&A portion. Feel free to continue doing that. We've got lots of good questions already. And we're going to get to as many as we can in the next 11 minutes or so. Okay, let's start with a first question. Let's see. I have a question for US Steel. Are there any lessons learned or best practices that you could share from developing your roadmap to 2050? Like, do you have any suggestions for how the researchers in the audience may be able to support other companies or industries when it comes to road mapping?
What we've done, and when we developed our roadmap to both 2030 and our net zero to 2050, was to take a look at the technologies that are commercially viable either today or in the near future, and incorporate those into our strategic decisions. As Dan mentioned, we're going to over double his capacity to 6 million tons in an EAF. That's part of it. The other part is carbon capture, and not just sequestration, but reuse. How, if we have to have carbon in the process, such as the integrated route, how can we take that out of the process gases and then make an alternative building material or some way to reuse that carbon dioxide in another process? So it's very important to look in our journey, and as Hannah talked about, hydrogen. Hydrogen today, whether it's gray, which is very economical, but we're excited about blue, we're excited about green. We've gotten involved in the Pittsburgh area and the tri-state regions on a hydrogen hub and an energy hub with players such as EQT, with Equinor, with Shell Polymers. So a number of companies that either need hydrogen, produce hydrogen, or can benefit from CO2 removal or sequestration or reuse are getting together to form these communities to better assess the values of this. And as Hannah mentioned, it's not just as a reductant for us. Absolutely, we have iron ore mines, and we have a lot of iron ore to yet to uncover. So we can produce the iron ore, as she showed in that one slide. We have to be prudent. We have to be able to take the hot briquetted iron or the direct reduced iron while it's hot and introduce it into the electric arc furnace. The other part, as Dan mentioned, we're up to 100% scrap, right? How can we preheat our scrap in an economically viable process? His video showed that scrap bucket with 190 tons of scrap. The higher the temperature of the scrap, the less electricity we have to add to get it melted to form our advanced high-strength steels and our green steels, right? So how can we take waste energy, waste thermal, and other forms and preheat all of our ingredients to their maximum point before we go into the melting process? A lot of opportunities.
Thanks, Kevin. Anything you want to add, Dan?
Yes, Kevin was instrumental, very instrumental in the plan that was rolled out for U.S. Steel, and I would tell you that it's extremely impressive. There's a lot of parts to it, and to Kevin's point, we looked at every single plant, every single process, where we needed to make improvements at, what was working good, what we needed to engineer or, think out of the box on. So I think when you look through that plan up to 2050, that's a large gap in time, right? I mean, that's 28 years from now, but it's laid at, in my mind, very, very, very nice from the standpoint that we're going to make improvements. We're going to do things like build another plant, that adds to our footprint. That's going to be a lot of low GHG decarbonization type process for the steel industry. And then we're going to work on our current plants and see what opportunities exist there. There's also a part of this where we have teams working on things that we've identified. Potentially there's not a solution yet, but we have time to do that. We have team members associated with these projects, very smart people in places that are coming to come up with solutions. So I think the roadmap is laid out extremely well from what I've seen. Kevin and the team that put it together, very, very impressive, but we'll get there for sure.
Thanks, Dan. Thanks, Kevin. Okay, I have another question for you guys. And this is a mix between questions we got from Mohammed Mutalib and also Benjamin Cross. And this is about trying to understand what exactly your energy needs are. So as researchers, we can understand what we're trying to design for. So the question is really, what is the energy usage profile of this steel making use case? So the sub bullets here were, does it require a continuous high power supply for extended periods of time, or pulses with long rest periods, or very much time varying current and power? And similarly, how far from the heat source can the heat be used without a significant drop off in temperature, for example?
Dan, what's your cycle arc on time?
Yeah, approximately 20 minutes. So to that point, we actually monitor all this internally, across a whole operation to see what we're pulling off the grid at one point in time to make sure we manage through it. The EAFs, to Kevin's point, are the largest consumers of energy on site here. So for about 20 minutes, that's probably the largest pool we have in here. But we monitor every part of the operation, how much electricity we use, and try to balance that across the board as we go through on a 24-hour basis.
And then thermal energy downstream, as you took us through our tour, we use thermal energy. We can use thermal energy in the finishing processes, such as our annealing operations, our galvanizing operations, and your new electrical steel line that you're going to build. And everybody should remember this. Steel isn't just a piece of the sector we have to abate. Steel is going to be a contributor to help the other sectors abate. His advanced high-strength steels, we can use half as much steel in a car and have the same amount of safety, which improves its mileage or improves the efficiency of the electric motor and battery combination, because we're developing very high-strength steels with ductility. Dan's also working on very good electrical steels for motors to improve motor efficiency. So as we abate our sector, we're taking the materials that we output into the other sectors.
Yeah, Kevin made me think of one more thing too. He's absolutely right. So our long-term plan, which I think will be shorter term to get there, is to know exactly, to tell customers how we made their steel at what hour of the day and what the power source was. We'll get to that point in that detail. And to try to roll out this scenario for the group to understand. So we'll make a heat of steel and make it into a coil that Kevin talked about that's going to one of these automotive suppliers as high strength steel. Our vision is that that steel goes in back of an electric truck. We deliver it a half hour away to one of these automotive customers that we have. They take the steel, form it into an automobile, an electrical vehicle. We pick up the scrap they use out of their process, the yield loss, because they stamp out doors, panels, things like that within the process. We haul that scrap in the same truck back to our electric arc furnace and charge it again. So this is all what we refer to as a complete closed loop within the industry right now. And that's the ultimate vision to get to out of this facility.
Thank you, Dan. That's great. Okay, I'm going to move on to a question for Prakash and or Hannah. This is about energy storage needs for industries such as steelmaking. What are the unique energy storage characteristics, let's say, that thermal energy storage or hydrogen energy storage would be able to meet to actually support steelmaking?
I don't know, Hannah, do you want to go first or
Well, I can, maybe
happy
I'll
to.
take the hydrogen piece if you want to
Sure.
take the thermal energy storage piece, divide and conquer.
Yeah,
So
sounds
for
reasonable.
the hydrogen piece, what's really important is scale. A medium-sized facility is consuming something like 200 metric tons of hydrogen per day. That is a lot of hydrogen. That's more hydrogen than we've ever produced in one facility. As a reference, 50,000 tons of hydrogen per day could power like a fleet in LA of light duty vehicles. That's kind of the scale we're talking about. And now we're moving to 200. So this is a big deal. And we need to be able to power that hydrogen in a way that is going to also meet the requirements of the furnace. So the nice thing is having a little bit of hydrocarbon in that hydrogen is okay. A little bit of that doesn't matter too much. Like a fuel cell, you need very, very pure hydrogen. So we're starting to see that there's actually a sweet spot where if we store our hydrogen in a material like toluene that actually could be going into the DRI furnace, that can be okay. We don't have to have super high separations like we do with fuel cells. So we're starting to see we have all these materials that we've discovered for hydrogen storage. They haven't worked for light duty vehicles. They haven't worked for fuel cells. But with the iron facilities, we're starting to see a sweet spot. The other thing I just want to note is when you deliver hydrogen from the electrolyzer, it's at about 30 bar. It's at a good, beautiful sweet spot pressure where if you mix it with the top gas coming off of the furnace, you can actually avoid having a compressor. These things matter a lot when you're talking about the size of compressors to power a large facility. Now, if you have hydrogen coming from a storage system, it might be at something like 2 bar. So now you need a compressor to mix it with that top gas and bring it into a furnace. These are the kind of insights we would have never known about unless we actually do analysis and process modeling and starting to understand what are trade-offs. So there are some really interesting targets for hydrogen storage that we've never seen before for the light duty vehicle space.
And on the thermal energy storage side, I guess there's many sort of performance characteristics that are critical here. But I guess one thing I think of is natural gas is kind of the best energy storage device, right? It's available when you need it, at the temperatures you need it. It's fairly cheap. So I think thinking of thermal energy storage in terms of how can it compete against something as reliable and oftentimes, maybe not right now, cheap as natural gas, and develop and thinking about a system where it's not just a device, but it's charging and discharging, bringing the heat from where you want it, where it is, to the device, and then sending it back out to where you need to go. That sort of engineering design such that you can bring the cost of these systems to equity or at least close, and that's more of a deployment target, I guess, will be critical for its uptake. But I do see large sort of potential, and as I believe Kevin was talking about, capturing some of the heat using it elsewhere to reheat something. You saw the reheat furnaces, for example, where things are, the metal's dropping down in temperature and then coming back up for casting and rolling and things like that. How can we avoid some of those huge valleys and kind of keep things more constant so you're not losing all that energy that you spent already? I think thermal energy storage has a major role to play. And I think we get caught up on the high energy, high temperature. I think it's good because we want to abate as much as we can, but whatever we can do does help, right? I think to eliminate some of that. So those are some short answers and ideas there.
Okay, thanks guys. I know we're out of time. I want to try to get to one more question from the audience. This is from Cliff Ho at Sandia. Does the use of electric arc furnace yield any change in properties such as steel strength?
It does not. Our researchers that work with Dan Brown's team and Dan Brown team itself, we have found ways to take advantage of the residual elements in the scrap to help us build our chemistries for the new advanced high-strength steels. So we can take advantage of that. We do maintain that we can add pure iron in the form of pig iron or direct reduced iron as needed for certain grades that are finicky about residual elements. But why not take advantage of those residual elements as part of our alloying process and build that into our unique chemistries and then our thermomechanical process where we get the final products.
Excellent. Dan, is there anything you wanted to add to that one?
No, Kevin's spot on. You know, if you go back in the history of the mini mills, it's very interesting. You know, when the mini mills started up, they made rebar as their first product, right? Because what's rebar? It goes in the middle of concrete. You never see it again. You don't worry what it's like, with the properties, what it looks like, quality, anything. Over the years, the mini mills have gotten up to speed and can make just about anything that these integrated plants can do. To Kevin's point, I mean, at US Steel, we have a dynamic and dynamite research department that we're making high strength steel for automotive applications now that nobody ever thought could be made. So yes, the mini mills can make up to almost anything that the integrated plants can do at this point in time.
What a great way to end this. Dan, thank you all of you. Special thanks to Dan, Kevin, Hannah, and Prakash for taking us on this awesome field trip and sharing more about the research. Thanks to the audience for joining us today. And I also want to thank those who helped put this all together. Many people it took to make today's event a success, but I'd particularly like to thank my co-host Johanna at Slack, as well as Sarah Price and Marianne Fives at Berkeley Lab, who have been working behind the scenes tirelessly to stand up the series. So for everyone in the audience, in case you missed our first virtual field trip to the International Space Station, our second virtual field trip to a tribe using microgrids, or our third virtual field trip to a net zero home in the Bay Area, you can check them out at secretlifeofenergystorage.lbl.gov. And a recording of this field trip and information about upcoming ones will also be available on that website. And we'll also send an email to those who registered with those links as well. If you have ideas for other field trips, we'd love to hear from you, and we hope to see you at the next one. So on behalf of Berkeley Lab and Slack, thank you so much for joining us today.